Having said that, I should say that this talk was not really planned. Yesterday, one speaker was missing, and so I offered to give a presentation, which means that I will be using largely a presentation that I had somewhere in a drawer, of course, because it takes a bit more than a few hours after the conference dinner to construct a talk of something like 1 hour. So I will be talking about characterization and especially looking at the self-healing of materials and things that you should think about when you are studying these materials, when you're trying to develop these. My background is maybe not even really in material science originally. I started out with chemical kinetics, gas phase reaction kinetics, and then moved into polymerization kinetics and thermal analysis actually to study these. Our lab has been specialized in this for the past, I think, close to 40 years now. So we have a quite broad experience. We mainly focused on polymer materials, although I do have a colleague working on inorganic polymers, that means cements and geopolymers. So it's not always just the organic materials that we study. He did some work on the aging of bread not so long ago. So, of course, there are polymers in bread, but I wouldn't call it, let's say, just a polymer system. So we use thermal analysis and we develop methods, thermal analysis methods, to study materials, to get better insight in how they are behaving, how they are changing over time or as a function of temperature. And we try to, from these insights, and use those insights to develop better materials. We are in a faculty of engineering, so although we like the beauty of science, we also like the beauty of applying it to real-life systems and improving the world that is surrounding us. So I don't really, for those people that attended here all the days and eventually previous training schools and so on, I don't really need to introduce self-healing materials, but there may always be people online or here that haven't been at all these occasions. So very briefly, why are we even interested in developing self-healing materials? Well, it's on this side today. Of course, when you are looking at materials, things like reliability, durability, safety, maintenance costs all come into play. It's not only about having the right mechanical, electrical, dielectrical properties and so on. And so when we have these materials, very often, okay, we can enhance them, we can make them better, we can have better properties, and maybe they'll survive as a result a bit longer. But at some point, damage is accumulating in these materials, and very often then they fail in a rather catastrophic way. So from that viewpoint, self-healing materials started to be developed. Trying to go to materials that if you use them, that when they undergo some damage, that they would be able to self-heal, that they would be able to recover their properties, that they would be able to heal damages, local damages in the structure, and as a result that they would survive for a longer time. From an industrial viewpoint, I would say in the past 20, 30 years, this has not always been the objective. Companies have designed materials, designed structures so that they fail early enough. I'm sure we could make a mobile phone that lasts 10 years, but if people want to change it after 2, or maybe after 3, but you can force them to do it after 2 by making sure it fails after 2, then of course there's an economical benefit in this. With sustainability getting more important, this is going to change. There's going to be a benefit in being able to sell materials, to sell systems that can last longer, that can self-repair, and maybe it means that our economic environment also needs to change, to adapt, maybe not to sell the phone, but sell the time that you use the phone. So if it lasts 3 years, they don't need to give you a new one after 2, and you still pay. So these things can change, and I would say they are changing rapidly. It's not going to last another 20 years before having something that lasts longer will be beneficial over something that fails a bit earlier or at the design time. Now, when you think about self-healing materials, I will be talking about self-healing polymers because that's what we specialize in. But I noticed in the corridor there is a poster about self-healing concrete. So this idea is not only limited to polymers, but certainly the elastomeric polymers that we are working on are a very nice kind of materials in which you can create this self-healing behavior. Now, okay, why self-healing in robotics? Well, because not always things go the way you planned them to go. Yeah? And maybe Asimov didn't hurt himself too much this time when he dropped off the stairs. But if he repeats it and repeats it and repeats it, then there will be damage accumulating in systems. And at some point, Asimov will no longer walk. That's what we are interested for in the sense of self-healing materials, that we can heal this damage at an early stage and make sure that these materials or these systems keep working as they are intended. Although we often show fingers that are completely being cut, it's a very nice demonstration. Maybe that's not the kind of damage that we most urgently need to heal. Yeah, that's not maybe what the most important target is. But it's a very nice way to convince people that indeed these materials are self-healing. There's a whole range also of self-healing polymers. This slide has been shown on many other occasions, and I don't want to go into detail. What we are working on is systems that are dissociative. So that means that they link at lower temperatures, that when you damage them, that reversible bonds are being broken and that they can be restored. So it's one type of self-healing materials, and that's the one we use. Why do we use this one? Maybe not because I thought that would be the best material that there would ever be to make a self-healing elastomer, but it's a material in which we combine chemical reactions with the way how, let's say, changing conversions adapt properties, how the material is changing with temperature and with time as a result. And so that's certainly a system where we could exploit the knowledge that we already had in relation to reaction kinetics, modeling of reaction kinetics based on thermal analysis and so on. So, principle of this system, as most of you are aware of, we have thermal reversible networks with Diels-Alder adducts inside. So bonds that are formed by Diels-Alder reaction between a furan and a malemite group. And if you form them, it's an exothermal reaction. That means that when you start heating up these materials, that this equilibrium, that this reaction equilibrium will shift to the unbound state. Not completely unbound immediately, it's an equilibrium that changes. So you go from a state that is highly bound to a state that is much less bound. But that means that you go from, if you design it well, that you can go from a network state to a liquid state. Somewhere in between, it will go through the degelation transition. So that means that although these are covalently linked elastomers, like classical cross-linked vulcanized rubber, for example, that although these are chemically cross-linked networks, that by heating them up, that you can make them flow, that you can reprocess them. So that means that you can cast them into a film, that you can cut them up, make filaments out of them, dissolve them again, or press them again into a sheet, do this kind of as many times as you like. somewhat limited by site reactions that will always be there. But it also means that you can use these filaments to go to things like 3D printing, which in the context of robotics is of course very interesting because it gives you the opportunity to redesign your sensors, redesign your actuators, see how the material properties should be tuned to make an optimal actuator and then reprint it and so on. We can make these hands with it. We are focusing on grippers on the moment because again, it's a very nice demonstration system to show what you can do. And it's definitely self-healing. You can cut it up, you can slice it, you can puncture it, you can put too much pressure on it, you can blow it up, and you can recover the properties. These are response curves, so meaning bonding angle of the actuator as a function of overpressure for different kinds of damage that were applied, including the more severe type at the lower end here. We can heal all these damages and get a system that functions again in the way that it was originally doing it. Now, when you design these self-healing materials, but also when you test them and you test their healing capacity, there are a number of questions that you should ask yourself. First one is, what property are we actually interested in? Self-healing means that you're healing the material with a certain target. So you might be healing mechanical properties, but there are certainly other options. Then you want to heal something. That means that first you need to damage it. What type of damage is relevant? For the material, for the application that you are going to use the material in. Depending on the application that you use in elastomer in, you will have different types of damage. Of course, some of them will be more common, others will be maybe more application related. When you want to introduce damage, you need to do it in a controlled way, because if every time the damage is different, okay, there are of course statistical ways to start analyzing this, but things like tensile curves until failure, you don't want to do 1,000 times, because you have to mount these samples manually. If you have to do it 1,000 times for every material we design, then we definitely need many more PhD students than we have now. And we already have quite a few working on this topic. And then, of course, once it's damaged, it's how do you measure the healing? How do you quantify it? You have different ways to do this, and some of them look very good on paper, but might not be so, or not be as performant as they seem when you look at it in real life. So let me dive into the first question. What properties would we like to heal? Probably quite a few of you have a mechanical engineering background. And if you think about the robot, probably the first thing you think is, okay, I want to get the same stiffness, I want to get the same modulus. Might be the case, but of course, that's not the only thing. You might measure de Young's modulus in the first few % of strain that you apply to the material. While in your application, it might go to larger strains. And so then, of course, the fracture properties, fracture stress, fracture strain, actually the tensile test curve in all its details might actually become important. But there are a lot of other properties that could be relevant. Could be a surface energy or a surface composition that is relevant. When you work on coatings, it's quite likely the corrosion protection that you are looking for. Electrical conductivity in other systems can be important. Once you go to sensors, for example, that becomes quite evident. So there are a lot of targets that we might be aiming for. I, at some point, worked on printing plates, lithographic printing plates that you irradiate with a laser. And the first thing the company told us, yeah, these are the irradiation conditions, and You should be able to get sufficient contrast between hydrophilic and hydrophobic regions to be able to print. About 4 years later, at the end of the project, there was a list of 13 other properties that were important for printing plates. It's never about one property that your material should meet. It's always about a combination of properties, even if you stay with very simple systems. But if we aim for multifunctional materials, then this only makes the target or the number of targets maybe larger in number and more difficult to reach, because you will want to heal everything. If you have a sensor, you will want to heal its electrical properties, its electrical behavior, but also its mechanical behavior and so on. Now, to show you also other things than the systems that we worked on, I'll show you an example of surface properties. In this case, surface hydrophilicity. It's a material system that was developed at the Technical University of Eindhoven. And so what they wanted to do, the problem that they had is that, okay, you have things like lenses for glasses, for example, and you might want to make them hydrophilic to make sure that if water droplets come on it, that the film spreads and that you don't have the diffraction of light on the small water droplets, and everything stays clear. But of course, if you do that by something like a plasma treatment or a corona treatment, which you could use to make the surface of a hydrophobic material more hydrophilic, you have a very thin layer, nanometer thickness layer, that you actually change in composition, and that over time, through wear, will disappear. And then, of course, your function is gone. So what they wanted to do was to make sure that you wouldn't only at the start have a hydrophilic layer that was on top of that material. What they did was anchoring hydrophilic chains onto the network and making sure then when you expose it to water, spontaneously they will migrate. The ones close to the surface will migrate to it and will make it hydrophilic. But of course, if that surface layer is removed, you want to make sure that it's replenished again, that new chains will come there, that you didn't just remove the dangling chains and hydrophobicity is there again. So they designed material, they made sure that okay, the properties, the length of the chains, the number of the chains were such that you have this surface replenishment, and that whenever you cut the surface, that whenever a surface layer is removed, that new material, new hydrophilic chains come up to the surface, and that you retain that hydrophilic behavior that you were aiming for. We did some work on corrosion protection, although these are results from another group. They made a shape memory polymer, shape memory to be able to close a cut or a crack that you make into the material with a shape memory response. And they included microspheres with a healing agent to help this shape memory response, and with a corrosion inhibitor to make sure that, as long as that didn't happen yet, that your metal that is underneath stays corrosion protected. These are measurements done with scanning electrochemical microscopy. And you can see that, okay, in the original material system, that you all the time have an oxygen reduction current. So corrosion processes are happening at the surface. And that by going to the triple system, so with all the different corrosion or all the different healing measures taken into account, that you can indeed cut the material, have it sealed spontaneously, in the presence of a corrosion inhibitor, to make sure that corrosion is not occurring, at least in the first something like 14 days that they tested it. This is a microscopic evaluation of self-healing. Yeah. Something I didn't say, but of course, you also need to consider the scale at which you are going to study these healing processes. This is a very local way to do it. It means that you have to do it for quite a few of these damages to get a kind of statistic evaluation of what is really happening in these small local zones. But of course, you can also put multiple scratches on your surface and use electrochemical impedance spectroscopy, so the macroscopic variant, to then study the corrosion behavior and indeed also to observe in this case that you get a quite nice corrosion protection with this triple healing system. Now, the next question is, how do we quantify it? Here, the answer could be, okay, you look at the corrosion barrier properties of this layer and you use this as a measure for self-healing, but you could also look at the crack and the crack depth and see how that gets sealed and take that as a measure. Or you could study the mechanical properties of this coating and use those as a measure for self-healing. So you will need to choose which property that you would like to follow. And then you need to look at what kind of damage needs to be healed. That will depend on the application, and I will just highlight this with examples from coatings and from bulk. When you look at a coating, scratches are one of the most common kinds of failures, of course. When you start applying them, you need to do this in a controlled way. So you will need to control the size of the scratches that you are applying, the width of the scratches, the depth of the scratches. Are they going to the metal or not? Are they going through the oxide layer or another layer that you put on the surface of the metal or not? All this will influence the way how the system will behave during the healing and will influence the results of what you get. But of course, these are not the only kinds of damage. You could also think of things like delamination happening as a result of maybe an impact, maybe bending, maybe a difference in thermal expansion coefficient of your metal and the coating that is on top of it. So for each material system, you will need to look at what is most important for the system and for the application in which it is going to be used. You can make scratches in a controlled way. You can do that with nanolithography and then make the symbol of your university disappear. It's a very nice way to see it. But it's maybe not the most quantitative way to show that you have a self-sealing or a self-healing system in this case. You can use scratch testers to apply controlled forces and with a controlled speed drag scratches through your material. And in that way, you get a controlled kind of damage, at least inside that material. Because if you start comparing materials, then with the same settings of force and speed, you might not make the same kind of damage. So if you want to study the healing of the same type of damage for different materials, you will need to adjust the conditions in which that damage is made, very likely. For delamination and microcracks, typically things like impacts and bending tests can be done to create these damages, but they will give you a limited amount of control over the location and over the size of the cracks or the damages that you are making. So it's a very controlled test. You can go to ASTM or ISO to look up the conditions under which to do it. So the source of the damage is the same, but the result will be very different from sample to sample even, but certainly also from material to material. Now, from a robotics viewpoint, you might be more interested actually in bulk properties. There, I just made let's say a kind of an overview of a few different polymer systems that you could study. Of course, if you go to thermosets, and I mean glassy thermosets at room temperature or at application temperature, then microcracks and crazing. So the cracks that you see appearing if you have a polystyrene or a plexiglass box and you push too hard on it, it will typically not shatter into pieces immediately, but first you will have these cracks developing in the material. So you can induce these by mechanical loads that are close to the fracture limit, or by bending it up to close to its bending fracture limits. But you need to realize that when you do this on samples that you made yourself in the lab, that typically when you do fracture tests, that you do something like 10 to get a more or less relevant statistical average out of these measurements. And that when you try to, for example, load a sample up to 80% of its average fracture stress, that is quite likely that quite some of your samples will fail during this test. Yeah? So you are trying to induce a limited amount of damage, but in reality, you might fracture quite some of the samples that you are trying to create damage in. Same goes for fatigue damage. Yeah? The average sample might live for 1 million cycles, but some of them will fail after 100,000. So it's not easy to induce, although you can apply in a controlled way the loading and the number of cycles and so on, it will not give you the same amount of damage each time. For films and elastomers, things like cuts and punctures, ruptures as a result of overpressuring are of course important, but also their fatigue damage is definitely one of the types of damage that is quite important. When you go to fiber reinforced composites, layered multi-material systems with different materials, different polymers, or really different kinds of materials inside, of course, again, delamination is very important, and again, quite difficult to introduce it in a very controlled way. What can you do? Okay, you can induce things like raising by tension or by bending. You can always take the same radius of a bar, fold it over the same angle, and make sure then that you do it with a large enough number of samples to get, let's say then, reasonable averages or a reasonable statistical evaluation of what you are trying to do. It's very difficult to quantify in the samples how many microcracks there are, where they are located, and what their size is. There are ways to do it. You can try to have pores, dyes, migrating, for example, into the polymer and accumulating in the damage, and then use imaging techniques to find out where they are located and so on. But you can imagine that that's not something that you would like to do in series for large numbers of samples and so on. For the cuts and the punctures, it's a bit easier. You can do what Seppe did. You take the same type of scalpel every time. You push it through the material, and you will, if you do it maybe with a controlled speed, if you really want to do it very nicely, but you will make almost the same type of cut each time you do it. In that case, you can easily decide where you made the crack, because different parts of an actuator will undergo different levels of strain and stresses. And so you will need to test the self-healing of an actuator for different places where you apply the damage. For thermosets, things like the tapered double cantilever beam were developed, where through the design, you make sure that you have the stresses located here where you have a small cut into the material. Your crack tip will actually start here and then grow into the material as you do kind of tensile test. So this was developed for thermosets, and to study then self-healing. They not only worked with, for example, capsules that were there with healing agent coming out of it, But they even did things like just putting the healing agent into the crack plane, letting it heal for some time as a first test to see whether that kind of healing agent might work or not. So there are certainly different ways to approach this, but okay, for the, let's say, the more glassy materials, this was a very nice test to do. And I will show some curves recorded with it a bit later. So as I said, for the elastomeric systems on sheets or on small bars or on fingers and so on, you can easily cut and puncture them in a controlled way and test them. Now, when I talk about testing the self-healing materials, very often we will be making these materials at a relatively small scale, usually at a larger scale than a typical polymer chemist would do it, not in a, let's say, a few grams, but maybe in a few tens of grams, but often not in a scale that you can make lots of actuators with them. Yeah, first we try to develop these materials, test them, and then when we think they are good, we try to turn them into actuators. Then there is always the question, yeah, what is the most relevant? When you test such an actuator, you might come to the conclusion that after a certain amount of healing time and heat in certain conditions, that, okay, the actuator is fully healed. It shows you exactly the same behavior here. But I would say this is the functionality, its functionality is fully recovered. That doesn't prove that the material was fully healed. Maybe if you try to increase the pressure up to closer to its limit that you determined in other experiments, maybe you'll find out that it's not yet fully healed and that there are still scars that are in a kind of intermediate state. They are closed, so you can pressurize the system, but it bursts at a much lower pressure than the maximum design pressure that you aimed for. So there is a difference between the two, and it will depend on what you're aiming for, maybe what is most relevant for you. We might be designing healing cycles with which you fully recover the properties that you target for, but with a much shorter healing cycle, you might be able to fully recover the functionality. How to quantify the healing, how to measure it. I mentioned that you could go to nanolithography for scratching the material and then to look at the healing of such scratches. You could really measure their size, measure their depth, their volume, and quantify it. That's what we did in these graphs. They date back quite some time, but nicely shows that you can start applying kinetic evaluations on, or time constant evaluations on this kind of healing behavior. Maybe this is more a sealing behavior than a healing behavior, because we show that the crack disappears. We don't show that the properties of the material go back to the same properties. In case of the tapered double cantilever beam, you get something like a tensile curve. You load a sample, you do it for a virgin material, you can do it for the self-healed material. You can quantify the, let's say, the mechanical response at small deformations. You can quantify it for let's say, the maximum levels of load that you can apply, or maximum displacements that you can apply, or of course you can integrate the curve and go to things like toughness. All of these will give you different measures, different healing efficiencies. Even healing efficiency is not something that is generally defined, for which there is only one definition available. You can find papers where they define it as the property of the healed material divided by the property of the virgin material. But I will show you in a minute that that might not be the most sensitive way to do it. We often use property recovery. That means that you actually look at how you are healing the damage. You take the property, the difference between the property of the virgin material and the damaged material, and you see how that difference is disappearing over time or with the healing schedules that you are applying. So this E could be a modulus, but it could also be corrosion barrier resistance or something like that. That's an animation that I forgot to take out. Now, if you consider measuring that healing, you could consider the following situation. You take a sample, you take a small testing bar, you cut it in two, put it back together again, you heal it under certain conditions, with or without pressure, without temperature and so on, but you heal it. And then we are going to measure the modulus of that bar, and we are going to compare it to the original modulus of the material. Question is, would you be pleased with 94% healing efficiency? Defined in the way of the former slide, that means that you recovered, you have a modulus that you measure, and that has 94% of the value that you originally had. Those of you not familiar with the question might think 94%, I mean, yeah, not too bad. But what does that actually mean, that 94%? Well, if you take a bar, you cut it for 30% in the middle, and then you apply a loading on it, a tensile loading. Well, of course, only here you will have a smaller cross-section, so only there you will have larger extensions. And of course, the rest of your material will be loaded and straining in the same way as when it was not damaged. So that means that the apparent modulus, maybe I should say the stiffness of the damaged beam, for a 30% cut is still 94% of its original value. So that means that when you put these two together again and you heal and you get 94% of your original modulus, that 30% of your crack plane, your cut plane, is actually probably not even in contact, or at least not bound together. Yeah? So the 94% healing looks very nice, but is not so nice. Of course, if you start from this state, you cut it 30% or you cut it 80%, you start somewhere here. And then you look at how that modulus is recovering. And you use the relative, let's say, evaluation with respect to the property after the damage that you applied. Then, of course, you get a much better measure of how actually your crack plane, how your cut plane is healing. When you purely look at the modulus, you also miss a lot of information. This is an evaluation with the virgin material, the damaged material, 80% cut, and then materials that were healed. And you see that the modulus, that the curve over the first 5–7% is overlapping. So the Young's modulus at small strains is completely healed. But then, of course, you see that the curves start deviating. What is happening is that the scar starts to open and starts to tear apart again. So yes, if you use this system in an application where you only go to 5% of strain, this is fine. It's healed for functionality, but it still takes a lot of time before it's fully healed. So certainly measuring stress strain curves up to failure gives you much more insight in the extent to which the material really healed. And of course, all these properties will give you a different measure of healing efficiency. You could use the modulus and get very nice values. You could use stresses or strains. They are already much lower. And if you use toughness, then you see that we healed, in this case, something like 20% instead of 90 or more percent that we have for the modulus. So be critical also when you see papers, when you review papers on these kind of topics, be critical on what is being evaluated. And of course, it needs to be seen in the light of the application for which it's being designed. Being critical just for being critical should never be the aim. Okay, let me see, how am I doing in time? When we look at our thermoreversible materials, kinetics is very important. What we are doing is we are breaking reversible bonds, and we are counting on chemical reactions to relink the material to recover the cross-linking that we wanted to have. Chemical kinetics, that means that there is a time scale involved in this. Yeah? If you heat up these materials very quickly, or maybe more importantly, if you cool them down too quickly, then the chemical kinetics will not be able to follow or will not be quick enough to make sure that you stay in chemical equilibrium, and that after cooling you recover 90–95% of the reversible bonds that you have in these materials. If you cool it too quickly, and too quickly in this case, for example, 10 degrees per minute, which is not that fast, will bring you to 60% of conversion, and then you will need time at room temperature, where the reactions are even slower, to make sure that it recovers to the 90%. If that 60% is good enough to give you the functional recovery of your actuator, that might be fine, but certainly it will not yet behave in the same way as a system that is fully recovered. Yeah? The cross-linking density is something like 60% of what it can be at the end. So even the modulus will not yet be the same. I will skip the study of the chemical kinetics. I always put it in because I always hope that I can also show some of these, but I will skip those in a view of still being able to take some questions. But what you do need to be aware of is that reaction kinetics, but also things like maybe crystallization kinetics or reorganization kinetics or diffusion kinetics, if you work with a healing system that is based on the release of a solvent or a plasticizer that then plasticizes the material and aids the shape memory response, you need to take into account these timescales when you think of the healing. That's actually why these reversible Bies-Hallers systems were kind of put into the bin at an early stage, because many people didn't take into account the chemical kinetics. And of course, then you test the material that is only partially cross-linked again, and it will not have the same properties. It will have probably much worse mechanical properties than the fully recovered material. So if you are working with reaction systems, try to get the kinetics, simulate them, not only to know how long you should let it heal, but also to know how during your experiments, how during storage, how as a function of environmental temperatures, your material might be changing. In our case, there is a very important effect of temperature on the healing conditions. Talked about damage and so on, but of course, there's also, in our case, healing time and temperature and cooling rates that will be important. In our case, the gel temperature is a very important one. When you go above it, the material will start flowing. Then it's, of course, easy to close large cracks and so on. But for an actuator, that's not what you want to do. Accidentally, sometimes it happens that the furnace goes a little bit out of control. As a result, your temperature goes 10 degrees above the intended temperature and your actuator flows away. You get a puddle of elastomer rather than a nice bending actuator. So also these properties you will need to measure to know in which conditions then the healing should be done. But in the end, of course, for the robotics guys, in the end, of course, the recovery, the functional recovery is maybe the most important. You should take into account maximum operating pressures and so on, so that you don't limit the range of operation that you can use for your system by healing it in the wrong conditions. And then, of course, yes, you need to test this for different kinds of damage. Don't only damage it in the easy places, also damage it in the zones of high stresses and high strains to get the more critical values. For some applications, you may need an immediate recovery. It's clear that with our systems in which slow kinetics are involved, it is not healing immediately, but that is not always the most critical aspect. You might think, I want to heal the damage right away. And of course, if you have very large damage, that is very interesting because you can put a finger back on and immediately start using it again. That would be very nice. But if you go back to Asimo and the stair problem, I mean, okay, if he drops off the stairs and the head drops off, then you will need to repair it immediately if you want to make it function again. But most likely you created local damage that you might not need to heal right away. And that might not matter whether it takes a day or a few days before it is healed, because I hope you will not make him drop off the stairs continuously. So let me close with kind of an overview of questions. So when you look at healing, when you evaluate this, consider the properties, all the properties that you might want to heal at an early stage, because if you design these materials or select these materials from what is available, you'd better take enough properties into account to avoid that you have to redo everything later on. Consider the types of damage. That means that you might need to consider the type of application that you're aiming for at an early stage, because the application might actually decide what kind of damage is most relevant. Consider how to create it in a controlled way, and if you cannot do that, consider how to statistically evaluate it to make sure that you get the right measures when you try to quantify it. You can quantify it locally, globally. You can consider different healing conditions. So also there, the relevant ones should be chosen. You might not want to put a robot with a lot of electronics for half a day at 90 degrees, because your electronics might not survive it, although our materials might. They might recover, actually. And you might want to consider at an early stage whether you are aiming for a functional recovery of your system or a full recovery of your material. With that, I would like to thank everyone who contributed to it. People mentioned here by names were the people who were involved in this at an early stage. There are many other people involved in this work these days. But okay, as I had to construct a presentation on short notice out of my own offer, I used mostly results that have been there for some time. I would like to thank Bram also and the people from the robotics group for a very nice collaboration, because robotics is a very nice demonstrator system for showing how this kind of materials works. And it gives us also a very nice, very nice targets to aim for when we are designing materials, because that's what we like to do, designing materials to reach certain properties, certain behaviors. And of course, I would like to thank all our partners, all our collaborators in the Smart and Shiro projects for a very nice collaboration. Although Corona intervened with it, I think there were a lot of contacts, a lot of long distance contacts, but nevertheless very fruitful contacts and collaborations. And it's very nice to finally be able to see all of you here live. Thank you.
Okay, thank you, Gib. It's very good overview, very interesting. We had some questions in the chat. Maybe we should start with them. And the first one is from Davide Felice, if I'm pronouncing it very well. And asking about considering the lamination. It often happens with FDM 3D printed parts. Is there any way to self-heal the common polymer filaments typically used? Or did you study any modified filament for these topics?
Yeah, so the filaments that we print, they have certainly an advantage in this sense, because the bonds that you will form between the layers that you print one after another will be the same bonds as are present in the rest of the material. The reason why you have delamination in FDM printed materials is that very often they are printed with thermoplastics. You put a hot layer, not really a hot string of molten thermoplastic onto one that is already cooled down and crystallized, and you will have very limited interdiffusion of the chains, and thus a very limited anchoring of the successive layers. We didn't try to modify thermoplastic filaments with this kind of reversible chemistries to make sure that we would be able to bond one layer onto the next one. I'm also not sure whether the flow of these materials would be sufficiently controlled to, let's say, do it. It has to go through a nozzle and things like this, or you might even use an extrusion printer to do this kind of printing. So I'm not sure it would be feasible with, let's say, classic FDM materials, but this kind of reversible networks exactly offers you the opportunity to have a very strong interlayer adhesion, or even to the extent that you can't distinguish anymore between the printing direction, and so the height of the printing and the directions in which you are printing. But with common polymers, no, we never modified them to achieve this.
Yeah. There's also another question from Serena, asking, do you usually study natural models, self-healing or self-sealing mechanisms present in natural tissues? And have you ever tried to use a combination of self-healing and self-healing, like pine trees release resin to seal the wound, then proceed to self-healing?
Yeah. The answer to that is no. It's not something we did. There have been groups that use, for example, the liquid that was used in a pneumatic system as a healing agent to make sure that when you have a crack or a puncture, that liquid would flow out, and then under the influence of either moisture or oxygen, I don't recall immediately which of the two, but that just by exposure to the atmospheric conditions, that it would polymerize and then again seal the damage. That's not something we tried, but that does indeed already exist in literature. Mm-hmm. In our case, the healing is really present inside the bulk of the material, and there is actually no need to have, let's say, a second healing agent to achieve the healing properties.
Yeah. And there's a very short practical question asked by Matthew, and he's asking, when the healing procedure is done at temperatures above the gel temperature and the material becomes viscoelastic that can flow, should we refer to the system as healing or recycling?
Yeah. Well, I would say that as long as you retain the original shape of the actuator, I would still call it healing. Mm-hmm. But that means that actually it cannot really flow. You should stay below the gel temperature, and although of course it is viscoelastic, but it's already viscoelastic, of course, at room temperature as well. Although it's getting more viscous in these conditions, it's not flowing. It's not really changing shape. So I would still call that self-healing. It's a stimuli responsive self-healing in that case, but I wouldn't call it recycling. I would call it recycling when you really take the finger, for example, you lost a part, we will not be able to just heal a new part onto it, then we might just reprocess the material. Lots of our fingers and so on have been made with material that was redissolved, recasted, or re-extruded, and just reused in that way. So yes, these materials offer a recycling opportunity, but I would say as long as you don't make it really flow and change shape, I would still call it healing. Mm-hmm. But what's in a name?
I think then we still have some very short questions.
Well, thanks so much, Geet. It's very interesting, especially in the beginning for the economic reason for damage. And that's remind me of this one lamp still operating like more than 100 years, still working till today. And companies make like a conclusion that we have to design on purpose lamp that fail faster. And in that sense, do you believe that we can design material that never damage and being soft?
Probably if you keep it in a sealed closet in the absence of oxygen and moisture and UV light and so on, you can have a material that kind of survives forever. And then even then forever is maybe too long. And I'm also not sure whether it even should be our aim to do that. Materials will always undergo processes and gradually change when they are used in the real world. And that means that we will not be able to design things like elastomers and make sure that they keep surviving forever. Just as we live longer and our skin that is exposed to UV light, although we protect it, is still aging and will change over time. In the same way, a material that is exposed to atmospheric conditions will gradually chemically change. We can make it more stable or less stable, but we will never make it able. I don't, from a theoretical thermodynamic and kinetic viewpoint, I don't think we can make it survive forever. But as I said, that might not even be needed, because things will happen with it when you use it. Parts will be lost, material will be removed from the surface and so on. And over time, a surface that was flat in the beginning, in which bacteria and other things might not be able to adhere very easily, might become rougher, and you might have more easily microbial contamination of the surface, for example, which in that sense, just a change of the surface topology might not be desirable. And if you remove materials, okay, you can reflow them maybe in certain conditions, but it's not obvious that you can do it in every kind of application. So.
Thank you. Also to the listeners and for a nice presentation.
Thank you very much.
If we have some extra questions, we can find it during the break. So now let's thank you again. And,